When there was change.
Created and then it was a but professor did suggest a change.
Okay. So what dimension? So I've had this thing and I decided people won't get lost. Thank you. Yeah, because I found out if I want to talk about all of them in depth, I have to take like 3 days. So yeah, in order to make it like in at most 20 minutes. To people keep leaving. Yeah, so I'm gonna go through it fairly quick again. So what is an algorithm? An algorithm is when you have an input, you want an output. An algorithm. So for example, if you have egg, want a sunny egg, the king is your algorithm. Right. So one way a problem set is to do it in a divide and conquer way. What it means is when you have a huge problem, you want to solve it in pieces. Solve a little bit and another little bit, and combine all of them together to answer your whole question. And merge sort is a basic kind of example for the divide and conquer method. What it does is to divide an array into small pieces recursively. So you can see it's smaller here, it's smaller. When it divided into one for each, it will start merging them. So in the end, you will get a array. So we've talked about Karatsuba multiplication. It's just another way to use to multiply numbers in arrays, and it's using a divide and conquer method. So now we have the big O notation. What's big O notation? Big O notation indicates that the runtime grows as the input size grows, in worst case. Means if you have a input of n, if it grows in a rate, and your algorithm runs slower than another algorithm, it will have a bigger big O notation function that shows it runs slower.
So I always got confused about this, about big O notation. We talk about the worst case.
Yeah, it's the worst case.
It just makes sense for me, but you know, for my experience, we talk about the quick sort. The worst case it should be n squared, right?
Yeah.
So we still say that algorithm is n solver. How does that happen?
Is it average So, case? yeah, so big O for quick sort. I'm okay. I can
The
talk about it right
average
now.
case is n-logn, but the worst case is n squared.
It's actually the average worst case. So, for example, the problem is quick sort. It has another random factor of it is given by the algorithm itself. And the big O, what the big O notation indicates is depends on your input. So if you choose the exact,
But you know what? By
Yeah.
implementation algorithm in an input, right? If I
Yeah.
choose, the pivot from the top, I can impact the signal notation.
yeah,
So
and it won't be on average.
no, if I implement like that way, it's highly possible. If the sort array have right sort, right, sort every time. But we didn't talk about like one point or square state.
I think you can state it in, which means the exact wrong time. So exact wrong means scale of it. So besides go notation, you have the notation and omega notation, which indicates how your algorithm scales. And when you're saying are always in the same case, sometimes it's theta to indicate it, but for computer scientists, to just use big O.
Which you mean
Yeah.
that even though for big sort, but there is some notation to evaluate implementation, which one has also that my implementation. We have two different implementations for the same sort, but we will have different scale. But then the
Okay.
implementation. You
Yeah.
choose the pivot random, but my implementation, I'm still, I choose the pivot from the top column. There's a way, my two implementation. The way all column quick sort.
So I assume that you start in a random place.
And usually, yes, that's what we're being taught all the time.
Yeah,
Not
and
having the
that's
specific, we access this first index time or the last index of the time.
that's the call quick and a nlogn on average is a random pivot.
Yeah, that's average.
Yeah.
But you said here, that's my question. In that case, we use average, not what.
Worst case. Yeah, and worst case only suggests that the worst case depending on the input. And the random part, so what is it from
Depending on input. Usually for always look at
for this average, average word comes from its dependency is not only on the input, it's also on the algorithm itself.
Just for everyone, what Kevin's explanation was saying is, let's say you go to a library and it's sorted A to Z, but your restriction is you have to go A, B, C all the time. And what if I always start at A, but I need to find Z, and I'm restricted to look one at a time? So that's like worst case all the time. It's always 26 steps to get to Z for thinking about it.
Yeah, we can talk about this. For the worst case, you don't technically have a same like input implementation because like for merge sort. Yeah, it's another. We can talk. We're starting our discussion on Tuesday. Yeah, so Strassen's subcubic matrix. So what it does is if you have two matrices that you want to dot them, from what you've learned in high school, I think, is for each element, right? You will do this. For example, there's 16. Then together, do this time this, plus this time this, plus this time this, plus this time this to get this one. And do it recursively to get all of them. So when you want to dot two matrices, you can also do it in this way, in a divide and conquer way, which you separate them into branches and dot the inside of them and merge them to get your final result. So what Strassen's algorithm does is it reduces the branches from 8 to 7, which gets a better big O notation. So this is just a fancy way to do it, but I'm not gonna go in detail. You can remember, just it's a faster way to do it. So for inversion counting algorithm, what's an inversion? An inversion is when you have a number, A is bigger than B, but goes before B in an array. There's an inversion here. So where will you use it? When you want to compare the similarity of two rankings to other rankings. So for example, when Amazon is recommending, so someone bought this, also buy this, what you may also like, they are comparing the similarities of your purchases. So using inversion counting, you can actually get a number for the similarity. So for example, we have an array like this and an array like this. So you can see it has one inversion here. It has one. The difference is, and if it's like, it will be 2 comparing to this one. So you can see the inversion is more. And you can implement it with merge sort. So cluster is very complicated, so I'm not going to explain, but it uses a conquer way to solve and finds the closest points and xy plane. So it's on your plane, and you want to find those closer than. comparison method to get notation for a divider algorithm. So it basically just solve the running time and get the notation with it. So quick sort. We've just discussed that you choose a random pivot and separate the array into two sub-arrays, which one of them are numbers that are smaller than the pivot and the other one is bigger. And it has average big O nlogn. Randomized selection. So when you want to find the median of an array, you can use randomized selection, which is a kind of alternative implementation of quicksort. And also a number with deterministic selection, which is fairly learn. So if you guys are interested. So for any comparison-based algorithm, there's a lower bound for it. And I show you this proof here, which if you are interested in, you can read it later. So graphs. A graph is a kind of data set which includes a set of vertices and a set of nodes. So just like you learned in software testing class, when you want to find a minimum cut of a graph, you'll find that there's a cut that divide the graph into two groups, but cutting the minimum edges. For example, in this graph, you've got a minimum cut here by 2. You also got 1 here. So Carter's random contraction algorithm find the minimum cuts of a graph, merging the vertices together and delete the self loop. For example, these two together, so it links 2 here and cut the 1, becomes self loop here. And
So the two nodes there becomes the one under.
so yeah, so you merge the two
Into
next
one.
to each other, yeah, connected to each other, and delete this one. So here's 2 lines.
How do you know?
decide?
Yeah.
Like
Yeah,
one-
they choose it randomly.
Okay.
And there's a problem for it because it will fail. But you can try it and try it many times, which if you want to do it one by one and try every pair, you have to have 2 to the n, worst case. But in this case, you can reduce it to n to the 2, to the power of 2.
Does it always choose the two nodes that are close to each other, or can it be like the two? Yeah.
Yeah.
Can it be this guys, or it has to be
Yeah, sure.
next to? Yeah,
Yeah, I mean, these guys are next to each other because they are
they're
linked.
connected.
Yeah, but you can't choose these two because they are not together.
They have to also connect to the other same node.
I mean, they have to connect to each other.
also connect to other same nodes. This one. This two, because these two connect to this one. Is that
Oh, they
no,
don't have to.
Don't have to.
They have to. Yeah. For some reason, it doesn't show, but there are two lines here. So you can get the minimum count too. And from some mathematical analysis, which I will not do here, you'll get the succeed probability of 1 over n squared, which makes it n to the power of 2.
Which means
N squared.
can lead me to the wrong.
Yeah, so you have to try it many times.
So does it give you a different answer every time?
Yeah.
Because it choose randomly.
Yeah. For example, if you
Yeah, that's the problem. So how can I know which
the lowest one.
Oh. Oh, you mean the minimum cut, the answer actually is correct, but it's not the minimum number. So you too many.
It may not be
But you
because
still don't know which one is the minimum number, right?
if you
How
try,
many times you have to try?
you have to try at most n to the n squared times.
Oh,
Yeah. But originally, you have to try 2 to the power of
still
yeah,
back
because it's like this way. If you have many dots, many vertices, you want to find dots of them. You will actually separate them into 2 groups. Find the connection in between. So here's a cut here. And for each point, it can be on the left group and the right group. So for point n, you can get 2 to the power of n kinds of combination because it can be all vertices on the side. So there are 2 cases that it can be. So it's actually this one, but big O notation don't consider this, so it's we go to the left.
Give me a quick reminder why what is that?
They used to find the minimum cut on the graph, which gives you some rather minor stuff on the graph. For example, they are not a combined idea to other ones, which you will consider they are trivial. So you cut them off, and you cut other trivial ones off. At the end, you will get only the most important ones that connect to most ideas.
So it's like you're removing the noise.
Yeah, or you're removing something that aren't the main things that you're looking for.
But the right answer. So like not even the one that you're not sure is the most important, right?
I think they will value into it.
I mean, each node of them can be like a link and web page. And if they're connected to most of the pages, they are considered important in this
Like that.
in this specific problem.
The page rank.
It's like yeah, it's like a
More
you can yeah. And it's the first course.
Oh, thank you. We can refresh a little bit to feel awake again.